for years from now.
We'll talk about jet quenching at the first Fermi over C. Please go ahead.
Okay, I would like to first thank the organizers for inviting me to provide this talk.
Sorry, Nestor.
Is it now full screen?
Perfect.
Okay.
Yes, thanks a lot.
Thank you. Sorry, I never get it clear. Okay, so I would like to thank the organizers for inviting me to provide this talk. And what I will talk after a brief introduction is basically why we think that we can get information using jet quenching about the very first stages of the collision that is not usually the main subject of jet quenching studies. So I will start with an introduction, then we will go to revise some observables that are sensitive to the initial stage of the collision, namely the very well-known RAA-V2 relation, and there have been talks that have touched this subject. Then I will talk a little about decaying particles, and then the theoretical challenges that trying to use jet quenching in this for this purpose poses. And first is how to introduce timing particle cascades, and second, how to model the interaction of a jet with a pre-equilibrium stage. And then I will summarize. Okay, so well, let's start with the standard picture that everybody is kind of managing, working with now. We have a very short stage in which we have the colliding nuclei producing something. Then we have a stage from this initial, I don't know how to call it, time to the hydrodynamization time, in which we have an equilibrium QGP. Then we have the near equilibrium QGP era, and then we have a hadron gas. And for that, we have the energy deposition, a rapid longitudinal expansion and equilibration. Then we have longitudinal transverse expansion, and then free streaming and hadron rescatterings. Okay, so for this, for any of these phases, we kind of have a theory or a model to deal with. For the initial stages, we have the nuclear wave function, nuclear PDFs, the CGC to model it at very low virtualities. Then for the initial stages, the dynamical picture that we have is the plasma, which is an overoccupied system. When the system becomes dilute enough, we do parton transport, effective kinetic theory, and then we connect to hydro, viscous hydro at this moment. And finally, we connect to a hadron cascade. And okay, so the question is whether we can apply this picture that is the standard picture in nucleus-nucleus collisions to small systems. So if we apply it, it means that we believe that there are near equilibrium QGP in collisions in a range of charge multiplicities per unit rapidity that go from 10 to 5,000. And if this is the case, if we believe so, how? So this is what we want to check and what we want to understand. Okay, I will go very briefly through this. There has been a talk about some recent developments concerning jet quenching by Krisek. So we have a wealth of observables in small systems that of quantities that are taken as QGP signals in nucleus. So we have several observables that usually are taken as collective hadronization or signatures of collective hadronization, signatures of collective expansion, hydro-like, direct photons, final state interactions that may be or may not be hydro. And then we have jet quenching that is absent. And this is basically speaking the whole in the whole picture. Why there is no observable jet quenching in these collisions. So as we have this picture, one easy idea is to try to address this by jet quenching. Traditionally, jet quenching aims at characterizing this phase, the near equilibrium QGP phase. There has been extractions of the, well, whatever quantity, the transfer coefficient or some parameter also related with the transfer coefficient by the jet escape collaboration, but by some other studies I'm not referring to, just putting the plots to illustrate that there has been a substantial effort and there is a substantial effort devoted to this characterization. But the point is whether we can do by understanding better jet quenching, not only in rough observables, but in some detail, whether we can make a full picture that contains the information of the different stages of a heavy ion collision. And this is the hope that, well, that sustains this talk. Okay, so why we think that we can use this? Well, because parton branch is a multi-scale process. And the energies may range from the TeV, from the hard scattering at the LHC, to GeV hadronization. You can see this very beautifully explained in the talk by Alba. But to be able to use this tool for time studies, we need first observables that are sensitive to what happens at the early stages. Because many observables, many traditional observables, let me call them this way, for example, RAA, tend to be dominated by late times. Or we think that they are dominated by late times, but it is near equilibrium QGP phase. And second, we have to understand how to formulate or relate a vacuum plus medium parton cascade with the time in which the medium evolves. And time, we will assume that some kind of equivalence between formation times and then evolution times. And let me note that vacuum cascade, there is no vacuum parton cascade currently formulated in time. The reason why it is in practical terms, no one has invested time enough because no one thought it was interesting. Okay, so let me note also that jet quenching may not be the only observable, and other observables that contain a lot of formation times, like quarkonium, may also be used for this purpose. Okay, so now let me go to the observables. As I said, I will deal with RAA V2 and then with decaying particles. Okay, well, since the very beginning of jet quenching in the 2000s, RAA has been related to high PTV2. And this is this high PTV2 was taken as a consequence of energy loss. Okay, so you have different amounts of matter in plane and out of plane, and that reflects in the yield of particles. So you can define the V2 simply by taking the difference, the normalized difference between the yield in this direction compared to the yield in that direction. You have the eccentricity. And then by using anything that you may think of as a spectrum. Here is a power-like spectrum. You can use also an exponential, provided that you take that the energy loss is much smaller than the PT, you can make an expansion. And for example, if you take that the energy loss is proportional to these quantities, to Q hat, to alpha S, and that would measure the strength of the interaction, and to L squared, then it's completely straightforward to realize that V2 is proportional to the eccentricity. It's also nice to see here that it's proportional to the strength of interactions, as it should be, but it is also has influence on the shape of the spectrum, and it decreases with PT. And this is, I mean, as simple as it can be. Okay, this is perfectly known by everybody. So let's go to a setup in which this is studied. So the standard setup relies on factorization. We have a factorization between the initial stage and the hard scattering element. And then we have some kind of energy loss that is parameterized by these quenching weights, and we have a medium modified fragmentation function. Well, in principle, this is a vacuum fragmentation function. And in the next slide, I will explain how we merge these two elements to give a medium modified fragmentation function. We compute this more or less state of the art at NLO, and the quenching weights, we use a Poissonian approximation. This is a standard Poissonian approximation that has been shown many times, and this is the single medium-induced gluon spectrum, this quantity here. That is usually taken in practical terms, considering approximations. And now there is a huge effort that has been explained in this workshop, that has been mentioned in this workshop, to improve this spectra by making them more exact. Well, so in principle, the most popular thing to do and the cheapest is the multiple soft scattering approximation. And it turns out that these quenching weights depend on two quantities. That can be chosen rather arbitrarily, but we have taken as the critical energy, the critical energy effective, or this parameter that is called R, that are basically line integrals of the Q hat along the trajectory of the parton. Yeah, you can take different moments. This is the first moment, and this is the second moment. Why these definitions? Well, they come motivated by scaling properties of the single gluon spectra, and this was discussed in the talk by Ajay. Okay, so now how we produce the medium modified fragmentation. Okay, we take a production point weighted by the densities, and we consider an arbitrary trajectory along this medium or along this overlap area and outside. This is the trajectory of the parton. And you simply take the line integral of the quenching weight multiplied by the effect that this quenching has on the a vacuum fragmentation function, and you simply integrate by the probability of production. Okay, so it's pretty simple, and then you take this quantity, go back here and plug instead of this. Okay. Well, the key point is interface with the medium, and the interface with the medium can be done in different ways, but the easiest way is to take that the Q hat along the trajectory is determined by the local properties of the medium, and these local properties are taken by from ideal or viscous event variability hydro that starts at some given time. And in this case, we will take that this is proportional to the energy density to the 3/4 by dimensional ratios. And then you have to model what happens before hydrodynamization. And okay, many options can be taken, that nothing happens, that there is no quenching. And then extrapolations of what happens in hydrogen at this time. Okay, actually in practical terms, whether you take this or this doesn't vary too much, simply because the value of Q hat is so large that it is really opaque, the medium. So it doesn't really vary too much whether you take one option or the other. So with this, in 2019, we computed the high PT azimuthal coefficients using the standard, the nowadays standard scalar product definition. And our strategy was to fix this parameter, that is the proportionality between the Q hat and the energy density, to describe our AA. For example, you can see here, and this is the kind of fit that we do, and we get our best value of K. And then we try to vary the time in which quenching is effective. So here we assume that quenching is effective from the very beginning. Here we assume that quenching is effective after 0.2 fermis, and then 0.6 fermis. Okay, and we try to describe it too, using event by event hydro. Okay, and the point is that the description is much better. Maybe the figure is not making the full justice to the reality, because the chi-square dramatically improves really. Okay, so in order to get a better description of the V2, you need to consider that the quenching is only effective after some time, after some long time, let's say 0.6 fermis. Okay, so this combination of observables becomes sensitive to what happens at the beginning. And let me say that these results have been checked for different centralities, variations of considering that the right variable to describe the early stages is temperature and not time, fragmentation function, single gluon spectra by going to the single opacity expansion, by varying the length, okay, the time which to switch off hydro, which is kind of mimicking a hadronic phase, etc. By the way, the same result was found, and actually earlier than in this work, in very different frameworks, because quenching was implicitly started at the same time as hydro, and hydro was started late. So quenching seems to be small for early times in all these frameworks. And okay, this thing is sometimes is called the joke in the egg, that there is no quenching in some region. So for some time, the partons here travel without seeing the medium. And this may suggest an explanation for the lack of quenching in small systems that has to be checked by other observables sensitive to times. But obviously it begs for a theoretical motivation. So let me go to the other idea. The other idea, that which is a very good idea, it was commented by Liliana yesterday, so I will go fast, is this idea that you may have particles that decay in the medium. And these particles may not interact strongly. Well, in the case of the top, is basically because of the huge mass. Then the W is obviously electroweak, and then you may have a QQ bar pair in singlet that, if you have set these ideas of coherence for some time, will not strongly interact with the medium because it's in singlet, it's compact. Okay, so well, this has been commented several times. Considering that you can vary or you can study tops with different boosts, with different PTs, you are sensitive to different times, long times, total times of the lifetime of the quark-gluon plasma. Okay, this is the kind of times that people was studying at relatively, this is a total time that you become sensitive to, okay? And well, there has been studies, I don't want to devote much time here, but the point is that in these studies, people have tried to address the question of how well you can determine the maximum lifetime of the quark-gluon plasma, of the interaction of the parton with the medium, depending on the amount of quenching that you have of the Q hat, and also depending on the obviously on the energy of the collision, because higher the energy, the more highest PT with a given statistical accuracy you will have. And this was one of the key motivations for running light ions beyond long shutdown 4 because of the highest luminosity. Okay, so controlling the boost of the top, we may become sensitive to smaller times. So we can address the question, when does this medium-induced energy loss starts to be effective? Okay, so is it possible to do something similar with other observables that are not tops? Maybe with jets, if we understand the space-time picture of a hadron cascade. And this is something that we anyway need for consistently considering vacuum and medium. So let me go to the last section of my talk, that is the theoretical challenges, timing parton cascades and how to model the interaction of a jet with a pre-equilibrium stages. Okay, so the role of time. Vacuum showers are not usually formulated in formation times, although in double logarithmic accuracy, whether you work in formation times, in K-perp squared, in M squared, or in angle, give exactly the same accuracy at double leading log. Okay, what is formation time? Well, formation time is simply the ratio between the energy of this guy and the virtuality that you have to admit that it has in order for this process to be achievable. Because obviously, if the three particles you want them to be on shell, you cannot do. So it's if you want, it's a theoretical definition. It can always be casted in different variables. Now, here I'm using kind of an Euclidean definition of this formation time, although you can do an analogous definition on the light cone, being the inverse of the minus component of this guy. Okay, so what I have said is that if you want to study the decay in the collinear limb of this particle with momenta p to A and B, it's equivalent in the double leading log approximation, whether you're doing any of these variables. And Z always decreases, but then you have decreasing angles, virtualities of transverse momenta, or increasing formation times. And of course, you're considering that in double leading log approximation, you have factorized successive emissions that you can cast into a Markovian process. And this is the basis of the parton branches. Okay. Well, but the equivalence between the different evolution variables is broken beyond the double leading log approximation. And this is as simple as by the different limits of the evolution. So if you want to put limits here and you put limits in K-perp, but here you put limits in angle, or here you put limits in formation time, then you have effects that go beyond double leading log. And for example, the loom plane that you get is slightly different, slightly or not so slightly. Okay, so these effects beyond double leading log that are immediately appearing when you formulate the cascade are broken, and the order in itself is broken. And let me note that in medium pictures are based on formation times that are considered to be equivalent to medium time, to the evolution of the medium, to the time in which you compute the evolution of the medium, and very, very often to double leading log reasoning. So I won't go into the details. Paul has explained this plot and has devoted a lot of time explaining how these different lines appear. But the key point in here is that all these lines, except this one that is hadronization, all these lines can be considered as timelines in the loom plane. So all these lines, this is the line in which the formation time is equal to the length. This is the line in which the formation time is equal to the median formation time, so to the typical time that it takes for a parton to decohere in the wave function of the incoming cloud in the medium. This point is simply when this time becomes equivalent to L, and okay, anyway, and this is the time dictated by the coherence time in the antenna setup. Okay, so all these lines are timelines. So we are always discussing times. Okay, so in order to correctly interface a vacuum shower with the medium, we need the shower to formulate the thing or translate it into times. And also to be sensitive to different times, we need to be able to reconstruct the shower information times using some algorithm. For example, the JD algorithm, that is an old algorithm used for A plus and minus, is exactly a formation time algorithm. While this algorithm that was proposed by Liliana is P equal to 1/2 algorithm, is also sensitive to inverse formation times. So it's also kind of a formation time algorithm. Okay. Well, and now the very last topic is we have these early stages. We have this overoccupied system, then we have the parton transport. And well, what happens here, we think we are able to cope with by, as I made the example before, how to interface between the quenching parameters and the medium properties. But we need to understand the quenching effects in the phase described by Glasma by parton transport. There's a lot of effort given here. I will mostly mention some effort in here. These phases may dominate completely the dynamics for small systems. So understanding what happens here is crucial for considering small systems. Okay, so let me mention something that will not be presented in this conference. That is a lattice solution of Yang-Mills for the Glasma phase. You put the solution of Yang-Mills into one equations, and you are able to compute the transport coefficient versus time just by computing the momentum broadening at a given time that you get. Okay, this is the momentum broadening versus the saturation scale in the Glasma phase. This is the momentum broadening that you get really when you go from initial time to hydrodynamization time. That tau zero here is 0.6 ferms. But funnily enough, to see here that the Q hat bias very strongly with time. So for very early times, you find that the Q hat is very large. This is values for different QSs, but then it decays very strongly. It reduces very strongly. Okay, and funnily enough, these guys found that the momentum broadening is stronger in the direction along the expansion, along the longitudinal expansion of the medium than compared to the transverse direction. And this is due to the structure of the fields. If someone is interested, we can comment, but this is basically due to the structure of the magnetic fields or the chromomagnetic fields versus the chromoelectric fields. Okay, and the asymmetry can be rather large, from a 50% to a factor almost 3. Then two things that will be presented this afternoon in the talk by Alina and with the talk by Hauksum is different ways of modeling or dealing with the momentum broadening of high energy partons in the Glasma and in an equilibrium phase, an anisotropic non-equilibrium phase in which the medium is basically modeled by Harter-Marlouf framework. Okay, so again, what you see in this first work, which is a proper time expansion that breaks at very late times, but still what you see is something that resembles very much, what these people found, an increase and then a decrease. And what they find is that the Q hat decreases for late times. For late times, consider the scale. So for times that are not immediately after the collision. What I found noticeable in the second work that will be explained this afternoon is that for low momenta, the momentum broadening is much smaller in the non-equilibrium situation, in the anisotropic situation compared to the equilibrium situation. So let me go to the summary. Okay, the early time dynamics before hydrodynamization is the largest unknown in our standard picture of heavy ion collisions. And this directly links to the small system problem. It seems to have a substantial impact on standard quenching observables, typically RAV2. So we have to look for further observables. And observables with delay or formation times, TOPS, Querconium may provide a handle. And jets are natural observables with many scales, momentum and time. So how can we use them? Okay, there are theoretical efforts to understand the effect of the initial dynamics, the Glassman non-equilibrium phase on energetic partons. And here, the key question is whether Q hat is increasing or decreasing with time before the very early stages of the collisions. And finally, time scales underline all our understanding of the medium modification of the QCD parton shower. We need to extend them to vacuum in order to get a consistent picture of both vacuum and medium showers. And there has been these talks by both Paul and Alba about improvements in parton showers. So with this, I conclude. Thank you very much to the organizers for the invitation and for organizing this very nice workshop, and to all of you for your attention. Thank you.
Thank you very much, Nestor, for this very nice overview. And we open the floor for questions. Please also at Zoom, raise your hands. We can. Liliana has a question.
Hi, Nestor. Thanks a lot for the talk. I was just wondering, I mean, can we see the picture of having some sort of Q hat calculation that it's very large, for instance, when you show your slide 20, that it's sizable still at the beginning, and we have then floated into this, indicating that we don't have kind of an effect at the very early stages. I mean,
do you mean what is the origin of this picture?
Yes, yes.
Well, basically, in these simulations, the system goes from overoccupied to less overoccupied extremely fast. So in principle, this lattice solution should include this famous instability for an isotropic system that leads to very, very rapid thermalization, or better to say isotropization. So in this picture, this kind of stabilities happen on these time scales, and they vary the occupancy of the system for given modes very, very fast. So that reflects very much on the strength of the fields. Okay, so the strength of the fields vary very, very, very rapidly with time, and that reflects on the Q hat. This is my understanding. Maybe there is someone in the audience that has a more clear picture.
Okay, I think James has a question here.
Yeah, thanks a lot for the nice talk. I had a question about this time formulation of the shower. So you describe how you can kind of write things or try to formulate things in terms of this formation time quantity. But in the end, if I understand correctly, that's still not exactly like the real time that the quark-gluon plasma will evolve in. So I was wondering, like, I mean, first of all, if that's correct, if you agree with that, there's kind of formulating things in formation time helps you get something closer to real time, but not really still solving like a full equation of motion of QFT. And your thoughts are like, if you agree with that, how good you think that is, or how close you think that can get us without trying to formulate things in like a fully real-time way?
Yeah, well, I don't have an answer for that. Indeed, it's not clear that formation time is exactly the same. Well, it's quite clear that it is not exactly the same as the usual time. But we're working on how, first on understanding how we can formulate a time picture in the vacuum. Forget about the medium. Is it possible to formulate a consistent picture of what happens in a shower that is not medium affected. So is it really sensible to try to do this in the vacuum? And then once we have this thing more or less clear in the vacuum, whether it is possible or not, hopefully it will be with some effort, then we will go to the medium. Because in the medium, you have to understand that everybody is formulating things in a time that implicitly assume that the times in the shower, in the medium induced shower, are times in the expansion of the medium. Okay, so let's take these rate equations. In these rate equations, the time for rates is the time for evolution. Yes, but then when you implement, for example, the LPM effect, this LPM effect is formulated in formation times. So this is pretty delicate and we have to understand it better. Yeah.
Right, I see. Yeah, that's very fascinating. Thank you.
Okay, we have a comment here from Siggy.
Yeah, maybe two questions. So firstly, so by comparing calculations of V2 with experiments, you get that there's very little Q hat at early stages. How do you square that with these Glassman calculations that get huge Q hat?
I have no idea. I mean, honestly speaking, I have no idea. First, one thing is that you have a huge Q hat, but if the Q hat is large for a very, very small time, then the effect is not very large. Okay, because obviously it's not only that the density is high, the density is high and the duration of this high density phase. So it's not impossible that you get a Q hat that is large, but it lasts so small, so little that you don't have much effect, honestly. Second, you have to take into account that the people is using values of QS that are, okay, maybe as a CGC guy, I shouldn't tell that, but Q hats are pretty optimistic on the large side. Okay, so assuming that you have a QS square of 4 GB squared is high. Okay, so see that by varying slightly the QS, this thing drops a factor 2 to 3. Okay, so all in all, I think there's a lot of work to do.
Okay.
That's my idea.
Yeah.
I don't have an explanation. Honestly speaking, I don't have an explanation.
Okay, sure. Yeah, I'll actually be talking about similar stuff this afternoon. And maybe another simple question. Do you think including vacuum-like emission would change your result for V2, would change this result that Q hat must be small at early times?
I don't really know. Again, this is, I can't speculate, but it will be mere speculations. So I prefer not to speculate. This is something that we have to make clear, and but I wouldn't say yes or no at this moment.
Okay. So just if I can permit one last question. So since this is my last session as a convener, I can just go over time and never be punished again. So, so I just wanted to ask like a phenomenological implication of this. So I guess as short times is not the same as small systems, right? I mean, you can have a small system, dilute system, where you wouldn't actually see effects of maybe saturation or Glasma or stuff like that. So how can we actually double check, and how can we somehow constrain the effects of these early stages? Yeah. Do you have any ideas? Yeah. Where will these effects show up in maybe unexpected places? I don't know.
Well, I mean, I think, okay, how to say, maybe you have heard, for example, something that comes to my mind of this very recent data by Atlas. There are preliminary data, but nevertheless, on excited epsilon states and excited on side 2s in proton-proton collisions. That it seems the epsilon states seem to be much more affected at higher multiplicities than the side 2s, which is in principle is a much bigger state, so it should be more strongly affected. Considering our usual intuition about what happens with quarkoning is counterintuitive. Okay, but maybe it has something to deal with formation times, because in principle, upsilons in the system, in the medium, in the collision should be formed before. Okay, so that's an idea. There may be some observables that are sensitive to this.
Okay.
Okay.
All right. I guess we have to think more together collectively. Good. Okay. So thanks a lot, Nestor, and all the speakers of this session.